For 10.4, we're going to talk about something called scalar multiplication. We've already talked about scalars very, very briefly at the beginning of this worksheet. So a scalar is just some kind of quantity, okay? It does not depend on direction. So it's a quantity that's just kind of like good as is. So we were talking earlier about like the speed of wind versus the speed of wind with a direction. Which one's a vector, which one's a scalar. So a scalar is just a quantity that does not depend on a direction. Okay, so it's like a numerical value that's kind of all by itself. Okay, scalars do not have direction, they're only magnitude. And so we kind of talked about a scalar as magnitude when we were talking about velocity. So we talked about, so like velocity is speed with a direction, okay? So the speed is the magnitude of velocity. So the speed is kind of like this scalar thing that can just be the magnitude, okay? So again, the scalar does not have direction. It's only magnitude. And a lot of times we will say that you can have a scalar quantity that does not depend on direction. So we could say the wind is traveling 10 miles an hour. The scalar is just 10, okay? It doesn't depend on direction. Now, if we change it and we say the wind is traveling 10 miles per hour north, then it's a vector, okay? So the scalar is just the number that stands by itself. It doesn't depend on the direction. Now, scalar multiplication means we're multiplying a vector by a scalar, okay? So what that does is it impacts the magnitude, okay? So if a scalar is positive, it impacts the magnitude, but not the direction. However, if a scalar is negative, it's certainly going to change the magnitude, okay? It'll either stretch or shrink the magnitude, but it'll also make the vector travel in the opposite direction. So if the scalar is negative, it'll impact the magnitude and direction. Okay, so please keep that in mind. Okay, now when you take a scalar and you multiply it by a vector, the result is still a vector. Okay, now here's what I kind of wish I had just done this second part because I feel like everything at the top is kind of like written out again at the bottom, so it feels a little redundant. But how does the magnitude change with scalar multiplication? We're going to let k be some scalar, okay? If k is greater than 1, the vector becomes longer, okay? So if we multiply some vector by a scalar k that is greater than 1, it's going to like stretch, it's going to elongate our vector, okay? If we have a scalar that is between 0 and 1, so it is positive but it has a value less than 1, then it shrinks the vector. It's going to make it shorter, okay? If k equals 0, the result is the 0 vector, okay? So if you multiply a vector by the scalar 0, you get the 0 vector. And then finally, if k is less than 0, meaning it's negative, then it reverses the direction and then the vector is still scaled by k. So you're still elongating or shrinking your vector depending on if k is less than 1 or if k is greater than 1. So basically, if the k is negative, that's going to flip the direction, but then whatever the number is still going to change the length of your vector. It's either going to shorten it or elongate it, okay? So that's really the heart and soul of what we need to know here. Now let's look kind of like at a quick sketched example. So let's say we have some vector v. Okay, so we've got the vector v. All right. And let's say we know we have to go 1, 2, 3. Let's do 2 and then 4. Let's do that. Okay. So let's say we have to go over 1, 2, and then up 1, 2, 3, 4. Okay. Let me change that completely. That is absolute garbage. So let's say we have an initial point. We go over 1, 2, and then we go up 1, 2, 3, 4. So that is going to be our vector v. Okay. So this is 2, this is 4. Okay. Well, if I wanted 2 times vector v, I have to change the horizontal and the vertical. So I have to multiply them both by 2. So if this is my initial point, I would have to go 1, 2, 3, 4, and then up 1, 2, 3, 4, 5, 6, 7, 8. So that is the vector 2v. Notice I went over 4. So 2 times 2 is 4. 4 times 2 is 8. Okay. Now, what if I wanted 1/2 times v? Okay. Well, instead of going to the right 2, I would just have to go half that distance. So I'd go to the right 1. And then instead of going up 4, I would just go up 2 because that's half the distance. So I would go up 1, 2. So that would be the vector 1/2 times v. Now, if I did 0 times v, I just get a point really. There's no vector. You get the 0 vector, which has a magnitude of 0 and it has no direction. So nothing really happens there. And then finally, negative. So let's say we had negative 2v. Well, if this is my initial point, I need to go to the left. 1, 2, 3, 4, and then down 1, 2, 3, 4, 5, 6, 7, 8. So it still changes the magnitude of v. It still elongates v, but it also changes its direction. So again, if k is negative, it's going to change the direction and it's either going to elongate or shorten v depending on what the scalar is, if it's less than 1 or if it's greater than 1. Okay, so that's kind of how scalar multiplication with vectors works. Okay, so let's look at a few examples. So we're going to talk, this is kind of like properties. I decided to save some words here. So based on what we know about multiplying real numbers, complete the following. Okay, well, if we have 0 times vector v, we already know from previous properties that we just get the 0 vector. So remember, the 0 vector has a magnitude of 0 and no defined direction. So if we multiply a vector by 0, we get the 0 vector back. Okay? If we take 1 times the vector, we just get the vector. Nothing changes. We have the same magnitude, same direction. Okay, now if we multiply a vector by -1, we have the same magnitude. We haven't changed our magnitude at all, but we did change the direction. So we have the opposite direction. Okay. Now let's say K1 and K2 are just going to be some kind of scalar. So we have scalar 1 plus scalar 2 times the vector v. Well, what this ends up doing is we can kind of treat this almost like a distributive property. We can take K1 times the vector v and add it to K2 times the vector v. So it doesn't really matter if you add the scalars first and then multiply it by that vector. Okay, or if you take the vector and elongate it at each part and then add it. So we can either add the two scalars and then elongate v all at once, or we can take v, we can elongate it by k, we can take v, elongate it by k2, and then we can add. We'll get the same results, okay? And then the same thing is true kind of in part E. We have k, which is going to be some scalar, times vector v plus vector w. So I can take k times vector v and then add it to k times vector w. So essentially what this means is if I take vector w and vector vector v and vector w, and I add them, okay, and then I elongate them, that would be the exact same thing as elongating v and then elongating w and then adding them. So you can either, one, add v and w and then elongate, or you can elongate v and elongate w and then add. You end up with the same resultant. Okay, so this is kind of the distributive property of scalar multiplication. Okay. And then finally for part F, we have K1 times, in parentheses, K2 times V. So this basically becomes the same thing as K1 times K2 times vector V. So you could elongate vector V by one of these scalars and then take that result and elongate it by the second scalar, or you could find the product of your scalars and then elongate V kind of all at once. So this is basically the associative property of scalar multiplication. Okay, so those are just some things that we happen to know about scalar multiplication, some properties we need to keep in mind. I think a lot of it is fairly intuitive. Just keep in mind when you're dealing with scalar multiplication, you are changing your magnitude. not necessarily your direction unless your scalar is negative, and then you're changing your direction. It's just flipping it in the opposite direction, okay? Now, for example 5 here, it says use the vectors given below to graph each of the resultant vectors. So we're going to do some more addition and subtraction, but now we're going to have scalar multiplication involved as well, okay? Now, in this case, we're using 3 different vectors. I didn't use the same 3 that I used in previous examples. Okay, I pulled this picture from somewhere, I don't remember where. So these are not color coded, and again, they don't really have the vector hats. They're kind of in bold print here, but just in case you want to make sure they're vectors, you can put the little hat thingies on them, okay? And then we'll find some way to color code them in just a bit, okay? So we have vector v. Let's make note of the motion, the movement that's happening here horizontally and vertically. So from our initial point to our terminal point, we go to the right 1, 2, 3, and then up 2. So we go to the right 3 and up 2, okay? For vector w, we would have to go down 1, 2, and then to the right 2. So again, from the initial point to the terminal point, down 2 to the right 2. And then for vector u, we would go to the right 1 and then up 1, 2, 3. So the right 1 and then up 3. Okay, so whenever you're doing geometric addition or subtraction or scalar multiplication with vectors, it's really helpful if you kind of figure out the initial motion or the initial movement of these vectors and then do your, let's call it arithmetic. I don't know. Okay. So for part A, we have vector, or we have 2 times vector v minus vector w. So let's kind of piece this apart. First of all, I'm going to rewrite this as addition. I'm going to think of this as 2 times vector v plus the opposite of vector w. Okay? So let's think about what 2 times vector v does. Well, vector v, we had to move it to the right 3, and then we had to go up 2. So if we're going to multiply that by a scalar multiple, we want to change the direction of both of those. We want to multiply both of those directions by 2. That'll elongate this by a factor of 2, okay? So that means we're going to go to the right 6, and then we're going to go up 4. So I took this 3, I multiplied it by 2. I took this 2, I multiplied it by 2. That's going to be my scalar multiplication of 2. And then the opposite of W. So originally W, we go down 2 and then to the right 2. So what we're going to do here is we're going to go to the left 2 and then we're going to go up 2. So we're changing both of those directions, okay? So instead of going down, we go up. Instead of going left, we go, or instead of going right, we go left, okay? So let's see what that's going to look like for us, okay? So I ended up giving you this like giant grid, and you don't really need anything like quite this big to do these, but you got all the space in the world right now, okay? So let's do some color coding here. Let's say we do V in red. Let's do W in purple. I think that was fairly consistent with what we had in the previous worksheet. And then we'll do that blue color for you. Okay, just so we can keep track of everything. Okay, so for 2v minus w, we're going to start by drawing 2 times vector v. So we're going to go red. And let's say we start, I don't know, let's just start here in the middle of what I have on my screen. So I'm going to go to the right 1, 2, 3, 4, 5, 6. Then I'm going to go up 1, 2, 3, 4. So that is vector. Whoopsie. I hate when Word tries to like straighten out my image. So that is 2 times V. Okay. Now from there, we want to add the opposite of W. Okay. So let's go to purple. So the opposite of W, we want to go from the terminal point on W, we want to go to the left 1, 2, and then up 1, 2. So we get this vector here. And then the resultant I'll do in black. So the resultant goes from the initial point of your first vector, so the initial point of V, to the terminal point of your second vector, which would be W. So this right here is the resultant, and this is 2V minus W. Okay, and there you have it. It's that simple. Okay, so I like to just sort of piece my pieces together first. So I kind of write out everything I need to do, and then I go to my picture. For me, that makes it a little easier. Okay, so for the part B, we have three vectors that we're dealing with now. So we're going to take vector v, we're going to add 2 times vector w, and then we're going to subtract vector u. Okay, so I'm going to rewrite this as addition. So I get vector v plus 2 times vector w plus the opposite of vector u. Okay, now I'm going to make note of what 2 times vector w is going to do. Remember, we're going to multiply both movements by 2. So we got to multiply the horizontal and then we got to multiply the vertical by 2. So looking at w, we would go down 2. So that means I'm going to go down 4. And then I would go to the right 2, which means I'm going to go to the right 4. So I'm going to go to the right 4 and then down 4. And then we also, whoops, I forgot my negative. We also need to look at what's going to happen with the opposite of u. We want to change both directions. So we're going to keep the numbers. We're just going to change the directions. So for u, we went to the right 1, and then we went up 3. So we're going to go to the left 1 and down 3. Okay, so we just change both of those directions. All right. So let's see what happens here. So let's see, V, we'll do it first. It's in red. So I'm going to start, I'm looking at my note. I want to make sure I get this like to where it doesn't go flying off the picture. So let's say we start here-ish. Let me get red actually. Okay, so we're going to start here-ish. Okay, now V, we go to the right 3 and then up 2. So I'm going to go over 1, 2, 3, and then up 1, 2. So that is vector V. And then from the terminal point of V, I want to take and draw 2 times vector W. So that means I want to go to the right 4, 1, 2, 3, 4, and then down 1, 2, 3, 4. So then I get this one right here. Let me scroll my picture down just a smidgen. Okay. And then I want to do the opposite of U, which we know means we go to the left 1 and then down 3. So let's see, we want U to be in this pretty blue color. So we're going to go, we can go down 3 and then to the left 1. We can go to the left 1 and then down 3. Doesn't really matter. So let's say we go down 1, 2, 3. So that is U, negative U. Let me go ahead and label 2W. Okay, and then my resultant I will do in black. So from the terminal side or the terminal point of negative u to the initial side, or I said that backwards, from the initial side of v to the terminal point of u. So from the initial point of v to the terminal point of u. So our resultant is like this. So this right here is v plus 2w plus the opposite of u. And there you have it. Okay. Not the worst thing you'll ever do. It's kind of fun. All right. So just remember your resultant goes from the initial point of your first vector to the terminal point of your last vector. And that's it for this video. Woohoo! Okay, next up we're going to talk about magnitude of vectors a little bit more thoroughly.